Good day, everyone. Our case study focuses on the Taman Bukit Permai landslide, which occurred at Taman Bukit Permai 2, Ampang Jaya, Selangor, on 10th of March 2022. This incident was a rainfall-induced landslide on a man-made slope that affected nearby residential areas and caused significant losses in terms of lives and infrastructure. This case highlights the importance of monitoring slope conditions and implementing early warning systems. The incident began with several days of continuous heavy rainfall, causing water infiltration into the residual granite soil and reducing slope stability. As the soil became saturated, internal soil movement and deformation gradually developed. On the 10th of March 2022, the slope suddenly collapsed, releasing soil, rocks, and debris into the residential area below. Following the incident, rescue and evacuation operations were immediately conducted by the authorities. The landslide was mainly caused by several factors. First was prolonged heavy rainfall, which saturated the soil and reduced its stability. Second, the area consisted of weak residual granite soil, which becomes more vulnerable when exposed to excessive moisture. Third, development near steep man-made slopes increased exposure of residential areas to slope failure risk. Lastly, there was an absence of continuous real-time monitoring and early warning systems, limiting the ability to detect early slope movement. The incident also produced major impacts. From the public safety aspect, the landslide caused 4 fatalities, displacement of 48 households, and psychological trauma among residents. For infrastructure damage, around 15 houses was affected, with 2 houses completely buried and 10 vehicles damaged or buried. The incident also caused long-term rehabilitation efforts and increased public concern regarding developments near hillside areas.
Literature review and suggested optoelectronic solutions. So firstly, for the analysis of the impact, the catastrophic slope failure at Taman Bukit Permai on March 10, 2022 exemplifies the devastating intersection of rapid urban development, vulnerable geological formations, and climate-induced extreme weather. The impacts can be analyzed across 3 core dimensions. So firstly is the public safety and health. The most severe consequence was the tragic loss of 4 lives. For the surviving residents, the psychological trauma of seeing a familiar hillside instantaneously morph into a fatal debris flow creates long-lasting mental health challenges. Secondly, is the infrastructure and property destruction. The physical toll was substantial, affecting 15 houses, with 2 homes being entirely buried under tons of residual granite soil and debris. Additionally, 10 vehicles were completely crushed or buried, highlighting the high velocity and destructive force of the rapid soil detachment. Thirdly is the community and socio-economic disruption. The incident fractured the local community. So following the declaration of the location as a disaster zone, authorities ordered the immediate evacuation of 48 neighbor houses along Jalan Teratai and Jalan Mega. So this situation displaced dozens of families, forced prolonged temporary sheltering, and triggered a severe decline in local property values due to the newly exposed geohazard vulnerabilities of the man-made slope. For our case study, we compared this to the Batang Kali landslide that occurred later that same year. So both tragedies shared a common denominator, which is the lack of real-time proactive telemetry. So historically, we've used point sensors like inclinometers. So think of this like a single thermometer in a giant room. If the fire starts in the corner where the thermometer is not, you won't know until the whole room is on fire. So these past systems are blind to any movement that happens between the sensors. So we are now seeing a shift toward optoelectronic solutions. We moved from fiber bright ratings, which were better but still limited, to distributed fiber optic sensing, DFOS. So this evolution allows us to monitor kilometers of land with a single strand of fiber, providing like a continuous nervous system for the slope. Our proposed solution is distributed strain sensing, DSS. The science behind this is basically it uses a phenomenon called Brillouin scattering. So imagine sending a laser pulse through a buried fiber optic cable. So as the light travels, a tiny portion of it scatters back to the source. If the slope moves even by a few millimeters, it stretches or strains that fiber. This strain changes the physical properties of the glass core, which in turn shifts the frequency of that backscattered light. Hence, the frequency shift is directly proportional to the mechanical strain on the soil. An active interrogator at the end of the line reads these frequency shifts thousands of times per second. It can tell us exactly where the strain is happening, down to the nearest meter, across the entire hillside. So how would this have changed the outcome of the tragedy at Taman Bukit Permai? So first, DSS can detect microstrains. Before a slope falls, the soil undergoes a creep, a tiny internal movements invisible to the human eye. So DSS would have flagged these shifts days before the 2022 collapse. Second, we propose an AI rainfall correlation model. Since we know rainfall intensity was the trigger in Ampang Jaya, our system integrates real-time rain gauge data. If the AI sees a high rainfall event paired with increasing strain on that fiber, it can trigger automated sirens and mobile alerts to residents. So for my conclusion, the Taman Bukit Permai tragedy was a failure in seeing the danger in time. So by implementing DSS, we transform a passive man-made slope into an intelligent, self-reporting structure that protects infrastructure and, most importantly, saves life.
Good day everyone, I am Nur Fazana and I will be presenting the problem statement and relevance of our optoelectronic solution. The tragic 2022 Taman Bukit Permai landslide highlighted 3 critical failures in traditional slope monitoring. The first point is point-based limitation. Conventional sensors only measure isolated points, leaving dangerous blind spots across a massive slope. Second is delayed detection. In residual granite soil, landslides happen rapidly during heavy rain. Visual cracks are often detected too late. Third is lack of predictive intelligence. Current systems are completely isolated. They fail to cross-reference physical soil strain with real-time weather data. To eliminate these blind spots, we must transition from vulnerable electronic sensors to photonic technology. Why must use optoelectronics? First, EMI immunity. Fiber optic cables use light, making them completely immune to lightning and electrical storms. Second, continuous coverage. A single fiber line acts as thousands of continuous sensors with 0 data gaps. Looking at the mechanism, our system uses distributed strain sensing, DSS, based on Brillouin scattering. According to the formula stated, when the soil shifts, it exerts mechanical strain on the buried fiber. This directly alters the backscattered light frequency. And active optoelectronic interrogator maps, this frequency shifts instantly, pinpointing the exact location of sub-centimeter soil movement in real time. Next, why is this critical? It comes down to three main pillars. First, preserving human lives. The 2022 incident tragically claimed 4 lives. Capturing microstrains early provides the vital hours needed for safe evacuation. Second, protecting dense infrastructure. With urban land scarcity, residential areas are built right next to man-made slopes. We must transform these hazards into smart slopes. Third, mitigating economic disaster. These landslides displaced 48 families and destroyed 15 homes. The cost of disaster response and property damage heavily outweighs the investment in proactive optoelectronic monitoring. Next, let's look at the effectiveness of our solution compared to traditional methods. In terms of coverage, traditional methods are discrete and point-based, while our DSS solution is fully distributed across the entire slope. In terms of resilience, electronics fail due to water or lightning, while fiber optics are chemically inert and immune to AMI. In terms of synchronization, all systems suffer from delayed logging, while our system streams data in real time. In terms of predictive power, most importantly, traditional methods are reactive, which means they measure damage after it occurs, while our solution is proactive, which means by feeding real-time rain and rainfall data into an AI, we can predict a slope collapse before it happens. In conclusion, passive monitoring is no longer enough. By leveraging optoelectronics, we can replace uncertainty with real-time, life-saving data.
When it comes to disaster prevention, we are aiming to transform light into life-saving time. Today, I will be presenting our proposed optoelectronic solution designed to turn a silent hill site into a vigilant nervous system. Our goal is to ensure that no threat goes unseen and that every single second is used to protect our community. We use two main technologies. One is distributed strain sensing DSS with ruggedized fiber optic cables. The other one is the optical dysdrometers, which are highly responsive, laser-based rain gauges. Let's begin with our first solution, which is the distributed strain sensing. It utilizes Brillouin optical time domain analysis. So how does this exactly work on a hillside? An interrogator unit continuously fires rapid laser pulses into the ruggedized fiber optic cables installed in the shallow trenches across the slope. Step 2. As the residual granite soil absorbs water and shifts, it exerts microscopic mechanical strain on these buried cables. Step 3. This physical stress alters the refractive index of the glass core. This optoelectronic shift changes the wavelength of the light that scatters back toward the source, a phenomenon known as Brillouin scattering. Step 4. The altered backscattered light pulse then travels back through the fiber to the interrogator unit. And last step, by analyzing the return time or time of flight, the system calculates the exact location and magnitude of the soil movement down to the millimeter. So, why is this technology necessary? Unlike the traditional discrete point sensors, which leaves behind blind spots, the DSS acts as a continuous meter-by-meter nervous system. It measures microstrains, allowing us to detect invisible soil creep hours or even days before major collapse occur. Furthermore, it is completely passive. The sensing cables require no electricity, which means that they are 100% immune to lightning strikes during thunderstorms. This continuous monitoring is essential in Malaysia, where weathered granitic terrains develop thick residual soil profiles that weaken rapidly upon water saturation. In the real world, this translates to life-saving predictive evacuations. Authorities can calculate structural failure, timeframes, and execute orderly evacuations of specific homes well before catastrophic collapse. Additionally, the data provides a continuous heat map for targeted preventative engineering, guiding the local council to install soil nails precisely where strain is highest. During post-incident operations, this surviving network also protects first responders by providing live structural integrity updates to the SAR commanders. Monitoring soil is crucial, but we must also monitor the trigger. That leads us to our second solution, which is the optical dysdrometers. So how does that work? Step 1. The unit establishes a continuous horizontal laser beam directed at paired optical receivers. Step 2. The raindrops then fall directly through this active laser beam path. Step 3. As the drops pass through, they cause measurable instantaneous fluctuations or occlusions in the light intensity reaching the receiver. Step 4. An internal microprocessor instantly analyzes these specific light interruptions to calculate the individual drop size, fall velocity, and exact rainfall intensity. And the last step, finally, this real-time zero-lag data is fed directly into the early warning system EWS to trigger potential evacuation alerts. The true power of the optical dysdrometer is its zero mechanical delay. Optical occlusion completely removes the mechanical lag found in standard tipping bucket systems, allowing sudden surges in rainfall intensity to be registered without delay. This is crucial for tropical zones prone to rapid explosive rainfall spikes. In weathered granitic regions, these sudden severe rainstorms directly trigger catastrophic landslides and debris flows, making immediate precipitation monitoring a necessity. By correlating this high temporal resolution rainfall data with the slope strain data from our DSS, we can deploy automated emergency protocols. If the optical dysdrometer detects an unexpected spike rainfall intensity, the EWS automatically escalates the risk from monitoring to pre-evacuation or standby, bypassing human administrative delays entirely. This correlation data provides residents with the crucial lead time needed. For example, a 15-minute warning before a threshold breach, to safely move their vehicles and evacuate before automated barriers lock down access roads. By combining internal strain sensing with external intensity tracking, we transition from reacting to disasters to predicting and preventing them. Thank you.